Okay, welcome back to the lectures on transform calculus, and in the last lecture we have studied a Fourier transform and its properties. So today we will continue this lecture for the application part, and we will discuss its application to partial differential equations. So the procedure is very similar what we have done in the case of Laplace transform. So for a given partial differential equation, we will apply the Fourier transform to both the side of the equation, and then this partial differential equation will be transformed to a simpler ordinary differential equation that we will solve, and at the end, by taking the inverse Fourier transform of the solution of this ordinary differential equation, we will arrive for the solution of the original partial differential equation. So before I go for the example, let me just summarize some formulas and the properties of the Fourier transform. So we have here the Fourier cosine and sine transform. So Fourier cosine transform was just denoted by f c hat alpha, and the definition was square root 2 over pi and integral 0 to infinity f u cos alpha u du, and its inverse. So Fourier cosine inverse of this f hat c will be just f x, and this is given by square root 2 over pi 0 to infinity f c hat alpha cos alpha x d alpha. Similarly, we have for the sine transform, instead of this cos alpha u we have sine alpha u, and similarly here this in place of cos alpha x we have sine alpha x d alpha. And then we studied this Fourier transform. So in this case, the Fourier transform of f we will also denote by this f hat alpha, because this is a function of alpha now, 1 over square root 2 pi and the integral over the whole axis, and we have f u e I alpha u du, and for the inverse we have again the same constant there, 1 over square root 2 pi and minus infinity to plus infinity, and then we have f hat alpha, and this will be e power minus I alpha x and the integral over this d alpha. So these are the main properties, or mainly the derivative theorem for the Fourier transform and Fourier cosine and sine transform. So first, for the Fourier cosine transform, we will use this for the first derivative, it will be alpha and Fourier sine transform of f and minus square root 2 over pi f 0, and this is the condition under which we got this result, that was that f x approaches to 0 as x approaches to infinity. For the second derivative, so Fourier cosine transform of the second derivative of f, we have minus square root 2 over pi f prime 0 minus alpha square Fourier cosine transform of f x, and in this case we have this result under the conditions that f x and f prime x, so the first derivative and the function itself, approaches to 0 as x approaches to 0. So these are the conditions other than the existence conditions we have. Similarly, for the sine, we have Fourier sine transform of f prime x is simply minus alpha Fourier cosine transform of f x, and Fourier sine transform of the double prime is square root 2 over pi alpha f 0 minus alpha square f sine transform of x. And for the Fourier transform, we have f prime x is equal to minus I alpha f the Fourier transform of f, and for the double prime we have minus alpha square f Fourier transform of f x, and in this case also that f x and f prime x approaches to 0 as absolute value of x approaches to infinity. So in these cases, so basically we will solve today the partial differential equations mainly, and in that case the function depends on two variables. but we will get this Fourier cosine or sine or Fourier transform with respect to one variable. So, the same formulas will hold, the other variable will be treated as constant. One more point I should mention here before we go for the examples, that we have to see for a particular problem that which one is applicable, whether we should apply the Fourier cosine transform or Fourier sine transform or the Fourier transform. So, one is clear that when the limit of the variable where we will be taking the Fourier transform is from minus infinity to plus infinity, then we will of course apply this Fourier transform. But if our range for the variable is given from 0 to infinity, then we have these two choices, either Fourier cosine transform or Fourier sine transform. So, in these cases, if we just look at the properties, the derivative properties here. So, for the Fourier cosine transform, for example, here in the double derivative we will be using for the second order partial differential equations. So, here this f prime 0 appears, whereas in this sine transform this f 0 appears, that the functional value at x is equal to 0, and this is the first derivative of that function at x is equal to 0. So, if this condition is given and the range of x is 0 to infinity, we will apply the sine transform, and if the first derivative, this condition is given, first derivative of 0 is whatever, if this is given, then we will apply the Fourier cosine transform. And Fourier transform when the limit when the range of that variable is from minus infinity to plus infinity. So, with this information we continue now for the different partial differential equations. So, a short introduction to partial differential equation I have already given in Laplace transform case. So, we will directly go to the application to PDEs. So, we will solve first the heat equation. And that is k del 2u over del x square del u over del t, and our limits are minus infinity to plus infinity, t is given positive. The boundary conditions are given u x t and u x x t both goes to 0 as absolute value of x goes to infinity, and the initial conditions are f x 0 as f x. So, we have only the first derivative here, so only one initial condition, and for x minus infinity to plus infinity. So, here the choice of the Fourier transform is clear. So, we will apply here the Fourier transform, because our variable is from minus infinity to plus infinity. Just remember, for the Laplace transform we we applied Laplace transform with respect to t, because t is always from 0 to infinity, t can vary from 0 to infinity, but now we will apply for the x variable from minus infinity to plus infinity. So, now taking Fourier transform, with respect to x. So, what we will get here with respect to x is a double derivative, and if we look at the table, so the double derivative is minus alpha square and the Fourier transform of f x. So, we have minus k alpha square, and Fourier transform I will denote by this alpha, and t will remain as it is, because we have taken with respect to this x, we have u x t. So, with respect to x we have taken, so this x is replaced by alpha, and the right hand side is d over dt will remain as it is, and the Fourier transform of this u will be u hat and alpha t. So, what we get, d u hat over dt plus k alpha square u hat alpha t is 0. Note that these boundary conditions for this problem we have already used here, because the Fourier transform of this double derivative minus alpha square u hat alpha t, we have used these two boundary conditions. So, the solution of this ODE will be just the characteristic equation, or here directly we can have this. So, du hat over, we can separate the variable and we will get this ln u hat. So, it is clear that the solution is e minus k alpha square, and the integral this side will be t, and we have some constant of integration. So, we know now the Fourier transform of the initial conditions given u x 0 is f x. So, Fourier transform of the initial condition, what we will get. So, u hat x will be alpha 0 and the Fourier transform of f x. So, f hat alpha. Now, we use this condition to get this constant. So, at t is equal to 0 we have f hat alpha. So, c is simply, so this implies that our c is f hat alpha, and then we apply this. So, we get u hat alpha t is f hat alpha and e minus k alpha square t. Now, we take the inverse Laplace transform, taking the inverse Fourier transform, not the Laplace, Fourier transform. What we get u x t, if we directly apply the definition of the inverse, what we will get f hat alpha e minus k alpha square t and e minus I alpha x d alpha. So, now you note that in this solution, if we leave this here, it is not a closed form at all, because in this integral we are using this Fourier transform of f of the initial condition. So, it is better to have a solution which does not have this Fourier transform. We may have the initial condition because that is given already, but we should not expect to have this Fourier transform. So, in order to avoid this, what we do, just recall the convolution theorem. So, we had the Fourier transform of f star g was square root 2 pi and f hat alpha and g hat alpha. So, if we take the Fourier inverse transform here, so f inverse of this, the multiplication of two Fourier transform like we have here. So, if we know the inverse Fourier transform of this, then we can get u x t just by the convolution of f and g. So, we let now that e minus k alpha square t be the Fourier transform of g x. So, then by the definition, what we have 1 over square root 2 pi and minus infinity to plus infinity e minus k alpha square t and e minus I alpha x d alpha. So, now we need to evaluate this integral. So, for this we consider a bit simplified form. So, consider the integral I, and then we will come back to this integral again, minus infinity to plus infinity e. So, here we have with respect to alpha. So, this is alpha square. So, we take here some constant times alpha square, this constant will be k t in our case, and minus just for the simplicity we take 2 b x and dx. So, here we have x and here also we have this alpha. So, what we do now, we try to put this in the whole square form. Okay, so, minus infinity to plus infinity e minus square root a x, this is the whole square, and p b over square root a will give us the multiplication of these and 2 times 2xb with minus. So, we have this term. What extra we have here? B square over a with minus. So, we have to add here b square over a and then dx. So, this e power b square by a we can take out of this integral. So, we have this integral e b square over a minus infinity to plus infinity minus square root a x plus b over square root a square and dx. Now, we substitute this a new variable a x plus b over square root a to t. So, that we have dx is equal to dt over square root a, and this implies that I is e b square over a, and we have minus infinity to plus infinity e minus this is t. So, we have t square and dx is dt over square root a. So, we have then this square root a we can take out of this integral. So, e b square over a and 1 over square root a, and this integral minus infinity to plus infinity minus t square dt, that is a Gaussian standard integral. We have square root pi the value. So, we got this integral, we had minus infinity to plus infinity e minus a x square minus 2 b x dx is equal to pi over a with the square root and e b square over a. So, if we let now, because we want to go back to this integral. So, we will choose our a as k t and this 2 b is I x. So, a is k t and this 2 b or b is I x by 2. So, we will get the our required integral, and we change this integral variable to alpha. So, e minus k t alpha square for this x square and minus 2 b. So, b is 2 b is I x. So, minus I x and this x we replace to alpha. So, d alpha, and we have pi over a is k t and we e b square is I square x square by 4. So, here we have then b square. So, that is minus x square over pi by a is k t. So, we have b square over a is k t. So, we have k t and this 4 comes from here. So, we have minus x square over 4 k t square root pi over k t. So, now we go back to this integral g x to equation 2. So, this we have evaluated and 1 over square root 2 pi will come. So, our g x is 1 over square root 2 pi, and we have square root pi and square root this k t and e minus x square over 4 k t. So, we simplify this square root pi will cancel out, and we have square root 2 k t from here, and we have e minus x square 4 k t. And now we can use the convolution theorem, because we had this u alpha t is f hat alpha, this the inverse transform we know, and now for this also we know that g x is the inverse transform of this. So, we will use the convolution theorem. So, using convolution theorem, we get u x t is 1 over square root 2 pi and this f x convolution with g x. So, this is 1 over square root 2 pi, and we have this convolution minus infinity to plus infinity f beta and g x minus beta d beta. So, 1 over square root 2 pi and minus infinity to plus infinity, we have f beta, and g beta is given 1 over 2 k t e minus x square. So, x is now x minus beta over 4 k t, and we have d beta. Again little simplification we can made if we take z is equal to minus x minus beta over 4 k t. So, this one here, so that we have the square again. So, this d z will be d beta over 4 k t. So, square root 2 is square root 2, we have this square root 4 k t, and this d beta will be, so we have 1 over square root pi u x t, because this square root 2 we can have with this square root 2. So, that we have exactly this term, and minus infinity to plus infinity f for the beta we have to get from here. So, that will be x plus a square root 4 k t and the z, and we have e minus z square d z. So, this is the solution of the problem, and we have in terms of the given function f. Okay, so now we take another problem where we will apply the Fourier sine or cosine transform. So, we have the problem that k del 2 u over del x square is equal to del u over del t, and x is between 0 and infinity, t is positive. So, the boundary conditions are given, u 0 t is u 0 for t positive or greater than or equal to 0, and the initial conditions are given, u x 0 is 0, and also that information del u and del u or del x and u both tend to 0 as x approaches to infinity. So, now the solution, and now we note that this u is specified at x is equal to 0. So, we have this boundary condition, u is given at 0, and our range for the x is 0 to infinity. So, we have choice for a cosine or sine transform, but this u is given. So, let us have a look again for these properties. So, if we have the cosine transform, then we need here f prime 0, but this information is not given in the problem. For the sine transform we need f 0. So, this is given. So, we will apply the sine transform. The choice is very clear. So, let me just also write down, since u is specified at x is equal to 0 and the x is between 0 to infinity, the Fourier sine transform is applicable to this problem. So, we take the Fourier transform, taking Fourier transform, Fourier sine transform, Fourier sine transform, what we get. So, this k is there, and for the del 2 u over del x square for the second derivative sine transform, square root 2 pi alpha f 0 and minus alpha square Fourier sine transform. So, we have alpha and square root 2 over pi, the function value at 0, that is this is u 0, it is given, minus we have alpha square and k is there already. So, k alpha square and the Fourier sine transform of u. So, Fourier sine transform of u, and the right hand side we have with respect to t. So, this will remain as it is, this differentiation, and we have the sine transform of u. So, now what we have, u s hat over dt plus k alpha square u s hat alpha t, and this is square root 2 over pi, and we have k alpha and u naught. Okay. Now, the we need to solve this equation. So, for that what we get the integrating factor. So, this is the linear equation, linear ordinary differential equation. So, integrating factor will be simply a k alpha square t, and then the solution we can get now e k alpha square t. On the right hand side we have 2 over pi k alpha u naught and e k alpha square t dt, and plus a constant, or we have u s hat. This we can take to the right hand side. So, k alpha square t, if we integrate this with respect to t, this is anyway a constant. So, we will get e k alpha square t over k alpha square. So, this k alpha will be cancelled and we will get 1 over alpha. So, what we have 2 over pi, you will get 1 over alpha, also u naught, and this e k alpha square t, and from this side we have with minus k alpha square t and c e minus k alpha square t. So, this u s is 2 over pi, and we have u naught over alpha plus c e minus k alpha square t. Now, the initial condition to get this constant, we have u x 0 is 0, that is given. If we take the Fourier transform with respect to x Fourier sine transform, so we will get alpha 0 is 0. So, with this condition, if we set here this t to 0, so this will be 1, and we have c naught. So, this implies that c naught is minus 2 over pi and u naught over alpha. So, we have this u s alpha t square root 2 over pi u naught over alpha. We take common because c is also having this factor. So, we have 1 minus e minus k alpha square t. So, we have this, and now we take the inverse sine inverse transform. So, we will get straight away this u x t, and that is 2 over pi, and we have 0 to infinity u s hat alpha t sine alpha x d alpha. So, we can substitute that, we will get 2 over pi, and also u naught will come 0 to infinity, we have sine alpha x over alpha, and we have 1 minus e minus k alpha square t and d alpha. So, this is the solution. The next problem, where we will see that we need to apply the cosine transform. So, next problem, solve del u over del t is k del 2 u over del x square, and subject to the conditions, we have u x 0 is 0 and for x greater than or equal to 0, and we have u x, the first derivative 0 t as minus mu, that is given for t positive, and u, and again this del u over del x, this both goes to 0 as x goes to infinity. So, we have again in the half range. So, we have possibility to apply Fourier cosine or Fourier sine transform, but this u x is given. So, we can apply only Fourier cosine transform, because we have this first derivative information there. So, taking this Fourier cosine transform, del u over del t and the k Fourier cosine transform of del 2u over del x square, what we get here d over dt, and this is u cosine, we denote it by this alpha t, and we have this k, and now this Fourier cosine of this. So, by that formula we have 2 over pi and u x at this 0 t and minus alpha square and Fourier cosine transform of u. So, we have d u hat c over dt, and this we will take, or this one, because it is a u hat only. So, k alpha square and u cosine transform, and here we have k, this is given minus mu. So, minus minus will be plus. So, k mu and this 2 over pi. Again we solve this linear equation. So, the integrating factor is e k alpha dt. So, we have e k alpha square t, and then we get the solution. So, I am writing this solution directly. So, that solution will be for that in terms of the u cosine transform, 2 over pi mu over alpha square e k alpha square t plus constant, and again this initial condition is given that u x 0 is 0. So, we will get u c hat alpha 0 is 0, and if we put it here we will get this c. So, this is 0 and this will be 1. So, c will be minus of this. So, then we get this u c hat is square root 2 over pi mu over alpha square 1 minus e minus k alpha square t. And now taking the inverse inverse cosine transform. So, inverse cosine transform now to get the answer u x t, that is 2 over pi and 0 to infinity u cosine alpha t and cos alpha x d alpha. So, we substitute here. So, we get 2 over pi, we get this mu and 0 to infinity cos alpha x over alpha square, and we have this 1 minus e minus k alpha square t and d alpha. So, these were the 3 applications where we have used the heat equation. The first was by applying the Fourier transform directly to the problem. In the second, we applied the Fourier sine transform depending on the conditions, and in the last example which we have just done, we applied the cosine transform again depending on the condition. So, we go now for the solution of wave equation. Solution of wave equation. So, we take this example that solve the wave equation del 2u over del t square c square del 2u over del x square, and x is given minus infinity to plus infinity. So, initial conditions that u x 0 is f x for this x, and u t x 0 is 0, and we have boundary conditions that u and del u over del x both goes to 0 as absolute value of x goes to infinity. So, we take the Fourier transform because this range is given from minus infinity to plus infinity. So, we have dt d2 over dt square and u hat alpha t c square, and for this we have simply minus alpha square and u hat alpha t. So, our equation is d2u hat over dt square plus c square alpha square u hat alpha t is equal to 0, and its general solution one can write u hat alpha t is the characteristic m square plus c square alpha square is equal to 0. So, the roots will be plus minus this c alpha I. So, for that we have the solution C 1 a constant and cos C alpha t plus C 2 sin C alpha t. So, now the initial conditions, the Fourier transform of initial condition, we have the u x 0 is f x, the first condition. So, here we get u hat alpha 0 is f hat alpha, and the second condition we have u t x 0 is equal to 0. So, from here we will get du hat over dt alpha, and as x approaches to or this t approaches to 0, and this is again 0. So, from the first condition, so our solution is this u hat alpha t c 1 cos and c 2 sin. So, when we put t is equal to 0, this is 0 and we have here 1. So, we get C 1 straight away from the first condition. We get C 1 is f hat alpha, and from the second condition, so we need to get the derivative first of this. So, du hat over dt is minus C 1 and sin C alpha t, and we have C alpha plus C 2, and for sin we have cosine now C alpha t, and again the derivative of this. So, C only C. So, C alpha. Now, again if we put this t to 0, in this case this will disappear, this is 1. So, this is 0. So, we have C 2 and C alpha, this is 1. So, in any case the C 2 is 0. So, we have u hat alpha t is f hat alpha and cos C alpha t. Now, we take the inverse Fourier transform, So, what we get u x t 1 over square root 2 pi minus infinity to plus infinity f hat alpha and cos C alpha t, and then we have minus I alpha x and d alpha. So, u x t is 1 over square root 2 pi, and this we take minus infinity to plus infinity f hat alpha as it is. This we write in terms of the again exponential function. So, I c alpha t plus e minus I c alpha t divided by 2 and e minus I alpha x d alpha. So, we have 1 over 2 and this 1 over square root 2 pi, then minus infinity to plus infinity f hat alpha, and this we combine into 1. So, we have e minus I alpha. So, we have x minus c t d alpha plus again this prefactor 2 pi 1 over square root 2 pi minus infinity to plus infinity. We have f hat alpha and e minus I alpha with this. So, we have x plus c t and d alpha. So, if we see now that half, and this is the definition of the Fourier inverse. So, we have minus I alpha, instead of x we have here x minus c t, here we have x plus c t. So, we will get f x minus c t plus f x plus c t, and this is also known as D'Alembert solution of the wave equation. So, just one more example for the wave equation, and then at the end we will solve the Laplace equation. So, we have del 2 u over del t square c square del 2 u over del x square, and this is given for t positive. So, in the half range we have this problem. So, initial conditions are u x 0 is f x and u t x 0 is g x, and boundary conditions are u 0 t. So, u is given at 0, and again the both u and del u over del x, they goes to 0 as x goes to infinity. So, now since the value of u is given, as per the formula we will apply the sine transform, because this function value is given at 0. So, we take the taking sine transform of the PDE. So, we get d2 over dt square, and sine transform of this u will denote by us hat alpha t. We have c square, and then by the derivative theorem we have square root 2 over pi alpha u 0 t and minus alpha square u s hat alpha t. So, this is d2 over dt square u hat s alpha t, and u 0 t is given 0. So, this term will disappear and this will come to the left hand side. This is alpha square c square, and we have u s hat alpha t is equal to 0. So, now again we can find its general solution, and that will be given by c1 cos c alpha t plus c2 and sine c alpha t. So, we use this initial conditions now to get these constants. So, what we have the first, so at t is equal to 0, the initial condition we have first u x alpha 0 is f hat alpha, because this was the initial condition. Now, u x 0 is equal to f x. So, we take the Fourier sine transform. So, we get u hat s alpha 0 and the Fourier transform of this f. And from the second one we have the derivative. So, d over dt and u s hat alpha 0 is g s hat alpha. So, from the first initial condition when we put t is equal to 0 in this, so this is 0. So, we have c1, this implies c1 is this given f s hat alpha. So, this is 1. For the second one we need to get the derivative of this first, and then we will put the t is equal to 0. So, we have du hat s over dt is minus c1 and cos will be sine c alpha t, and then we have c alpha plus c2 and cos so c alpha t, and we have c alpha. So, if we put t is equal to 0, this will disappear, this is 1, and this is g hat s alpha is equal to c2, and we have c alpha. So, c2 is g s hat alpha over c alpha, and c1 is this. So, we can get now the solution u s alpha t, that is f hat s alpha cos c alpha t, and plus we have g s hat alpha over the c alpha and then sine c alpha t. Now, we take the inverse. Taking inverse sine transform, we get u x t will be square root 2 over pi, we have 0 to infinity, and this function here. So, we have us hat alpha t and sin alpha x d alpha. So, this is our us alpha t and then multiplied by sin alpha x. So, we write this now. So, we have u x t as a square root 2 over pi, we have 0 to infinity, we have f s alpha and cos c alpha t sin alpha x in one term, plus we have g hat alpha over this c alpha and sin c alpha t and sin alpha x, then d alpha. Okay, so now we expand this because the two sin alpha and cos beta form. So, we take 2 over pi and we have 0 to infinity and this f s hat alpha over 2, and this will be now 2 times sin a cos b will be sin a plus b x plus c t alpha plus sin x minus c t alpha d alpha plus again here 2 over pi with that integral. We have 0 to infinity g hat alpha 2 c alpha. So, 2 sin a sin b, we have the cos terms, then cos a minus b or b minus a, does not matter. So, x minus c t we write and then minus cos a plus b. So, x plus c t alpha d alpha. Now, for the first term we can easily write in terms of f taking inverse sine transform, because it is given exactly in that form f s hat alpha and the sine and again this other term with the sine. So, we will get straight away f alpha, and here also this f x plus c t, and this will give x minus c t divided by 2, but for this term this alpha is appearing here. So, in this case what we take, consider a function g u. So, g u is the Fourier transform for inverse Fourier transform of this g hat alpha. So, we have 0 to infinity Fourier sine transform. So, g s hat alpha, this is all Fourier a sine transform, and then we have sine alpha u d alpha, and if we integrate this from x minus c t to x plus c t, g u d u 2 over pi, and we also integrate change the order of integration. So, first 0 to infinity will come g s hat alpha, and then this x minus c t to x plus c t will come, and sin alpha u d alpha. So, if we integrate this, we will get cos alpha u over alpha and then put the upper limit and the lower limit. So, what we get in this case, that this integral x minus c t to x plus c t g u d u is 2 over pi, we have 0 to infinity g hat s alpha over this alpha, we are getting exactly the term we need there. So, cos x minus c t alpha minus cos x plus c t alpha, and then we have d alpha. Thus, the solution is given by. So, if we just now go back to this we know what will be the inverse, what will be this, and here also we know now from this integral that this is equal to that. So, we take get the solution u x t is half here, and square root 2 over pi 0 to infinity f s hat alpha sin x plus c t, we will get the f x plus c t, and then for the second one we have x minus c t, f x minus Ct, and for the second term what we just arrived, it will be just x minus Ct over x plus Ct and gu du. So, this is the solution. Now, we go for the last example of this lecture, and that is the solution of Laplace equation. So, in this case we solve u x x plus u y y is equal to 0. It is given from minus infinity to plus infinity, y positive, and the boundary conditions are u x 0 is f x, again in the same range, and this is given that u is bounded as y approaches to infinity, and again u and del u over del x both goes to 0 as mod x goes to infinity. So, we take the Fourier transform both the side, we will get this transformed ordinary differential equation, and then I will directly write the after taking the Fourier transform, we will get d2 over dy2 u hat alpha y, and we get minus alpha square u hat alpha y is equal to 0, and its solution we have alpha y C1. So, with respect to x we have taken again this Fourier transform E alpha y plus C2 E minus alpha y, and the condition is given that u is bounded as y approaches to infinity, and this will imply straight away that this its Fourier transform and that we take with respect to x, not with respect to y, must be also bounded as y approaches to infinity. And this will tell us, because here we have this alpha y and minus alpha y, that C1 is 0 for alpha positive, because otherwise this will blow up. So, to have this boundedness, and this C2 will be 0 for alpha negative, in that case this will be unbounded. So, for this boundedness, so in any case, thus for any alpha what we can write, we can eliminate one constant there, because we are anyway getting this alpha y is some constant times alpha y, the absolute value of alpha y. We cannot get this alpha, because the C1 will be 0 if alpha is positive, and if alpha is negative, the C2 will be 0. So, what we have some constant and e power minus alpha y. Now, with the boundary condition, we have u hat alpha 0 is f hat alpha, this is given the boundary condition. We have taken the Fourier transform. So, as y 0 we will get the c. So, c will be f hat alpha, and now our solution of the transform ODE is f hat alpha and e minus alpha y. And now, we again apply the same trick to get this inverse, this convolution theorem, but we need to get the function, the Fourier inverse of this. So, let that g x is the Fourier inverse of e minus alpha y, and then we take as per the definition 1 over square root 2 pi minus infinity to plus infinity e minus alpha y e minus I alpha x d alpha, and then this we write cos alpha x and I sin alpha x. So, since this is the even function, and here with cos is also even function, and with this sine odd function, so this over the symmetric integral will be 0. So, we have 2 times 2 pi and 0 to infinity e minus alpha y, and cos alpha x will remain. And now, this we can have 2 over square root pi, because this will be square root 2 here, and we have 0 to infinity e minus alpha y cos alpha x, and this is a very simple integration. One can just get integrating by parts. So, we will get in this case g x as 2 over pi, and this will give us y over x square plus y square. So, this integral will give y over x square plus y square, and now we go back to the solution now, and that is the Fourier inverse of this f hat alpha and e minus alpha y. So, this was the g hat alpha, this is f hat alpha. So, by the convolution theorem we have 1 over square root 2 pi, and we have f and the convolution of this g. So, 1 over square root 2 pi and this convolution we can write down. So, we have 2 over pi, and because this g alpha we have this factor. So, we have taken this, and minus infinity to plus infinity f beta, we introduce this integrating variable, and then we have y over x, we replace this x by x minus beta for the convolution, x minus beta square plus y square, and we have this d beta. So, what we get u x y is 1 over pi, square root 2 will cancel, square root pi, we have 1 over pi, minus infinity to plus infinity, we have f beta y over x minus beta whole square plus y square d beta, and this solution is also known as the Poisson integral formula. So, that is here we complete the discussion on Fourier transform as well as on this rather introductory lectures on transform calculus, and we have mainly discussed the Fourier transform and the Laplace transform, and each topic was supplemented by various well chosen exercises. So, I hope that this lecture, which was rather introductory of course, will help to understand advanced topics in related areas. Thank you.